Okay, so welcome to this next video in the theory of probability. In this video what we're going to discuss is uncorrelated random variables. So uncorrelated random variables is the topic for this video. Uncorrelated random variables. Okay, right, so we have seen in the previous few videos the definition of correlation. We've seen that correlation of, let's say, two random variables x and y is defined to be equal to either the covariance of x and y divided by the standard deviation of x times the standard deviation of y, or you can define it as equal to the covariance of the standardized random variables x minus the expected value of x divided by the standard deviation of x, and with the standardized random variable for y minus the expected value of y divided by the standard deviation of y. Okay, so that's one of the two ways in which you can define correlation. Two random variables are said to be uncorrelated. So uncorrelated means that the correlation between them is equal to 0. So if this is equal to 0, then that's what uncorrelated implies, basically, that the correlation is equal to 0. So a great class of uncorrelated random variables are if the two random variables are independent. So if x and y are independent, then it implies that they are uncorrelated. So the intuition for this is that independent, they are uncorrelated. So let's go back to our intuitive example of where we have our abstract probability space, our abstract sample space rather, is everyone on the planet. So every human on the planet. Now, okay, so here we go. So here is every human on the planet. So we need two random variables which are going to be independent. So let's take height as one of them. Now we can't use mass because mass and height just aren't believably independent. So we need something else, some other numerical value associated with everyone. What about IQ? So we'll say IQ. So we've got some random variable I, which is again ascribing hopefully a non-negative number to everyone. And we have these two random variables which are ascribing these real numbers to people, and height is not generally viewed as being correlated with IQ. So basically, we might assume they are independent. And if they're independent, what that means is that knowing someone's height tells you absolutely no information about their IQ, their intelligence. And knowing their intelligence tells you absolutely nothing about their height. So basically the marginal distribution of intelligence is going to, basically the joint random variable is just going to be the probability the joint random variable is just going to be the, if you want to know the probability that your height is equal to some, let's say, little h, and your intelligence is equal to some little I, then that is just going to be equal to the probability that height is equal to little h times the probability that your intelligence is equal to little I, is the definition of independence in terms of probability spaces, abstract definitions. So that's what we mean by saying, that's intuitively what we mean by saying that these are independent. And now let's see why that corresponds to this number going to 0. Well, if h and I are independent, so if we take the correlation of h and I, then by definition this is equal to the covariance of h divided by divided by the standard deviation of h times the standard deviation of I. Okay, so the standard deviation of h and the standard deviation of I, you can work those out. The covariance, how do we work out the covariance of h and I? Well, one of the ways we can work it out is that it's the expected value of h times I minus the expected value of h times the expected value of I. But if h and I are independent, the expected value of h and I is just equal to the expected value of h times the expected value of I. So what we get is the expected value of h times the expected value of I, take away the expected value of h times the expected value of I, which is just equal to 0. So basically we get that the covariance is equal to 0. So if we work out what the correlation is, it's just the covariance 0 divided by some numbers which shouldn't be equal to 0. And basically what you get is 0, so the correlation is 0. So independent random variables are uncorrelated. Independence implies uncorrelated. Now, this is the point where people make mistakes. They begin to think that the other way round is true also. If you've got two random variables which are completely uncorrelated, surely that means they're independent. The answer is no, and remember that what this is just a formula. It is just someone's attempt at making a measure of the intuitive notion of correlation. It's a good measure, but it is just a formula that spits out a number. So don't confuse it for meaning independence. I don't confuse this number coming out as 0 as meaning independence. It means that this number has come out as 0. It does not mean independence. Okay, so I want to give you an example, a fantastic example, where the two random variables are utterly dependent. In fact, one is a function of the other, but you still get an uncorrelated value here. Okay, so let's say we have some abstract probability space, and I have a random variable z, which is going to ascribe real numbers to all of the points in here. And basically, what you find is that z is normally distributed. It's standard normally distributed. Z is the common notation for a random variable, which is going to be standard normally distributed. And basically, I want to create another random variable. Which is just going to be z squared, which is going to ascribe real numbers onto here. So this is a good practice at altering probability density functions here. What is this probability density function z squared? So remember what we are doing. We are ascribing, this random variable here is ascribing real numbers to everywhere on here. And the probability density function looks like the standard normal distribution. So here it is. You often see the notation phi of x, little phi, i.e. non-capital phi of x, given for the probability density function of the standard normal, and that's obviously given by the equation 1 over the square root of 2 pi e to the negative x squared over 2. That's the formula for the probability density function for the standard normal distribution. Okay, so every outcome in here is ascribed by this big random variable z some real number. So it might come over here, let's say. And now what I'm going to do is I'm going to create another random variable which is going to ascribe every outcome in here, not z of s, but z of s squared. So basically, all of the outcomes which were ascribed a negative real number are now going to be flipped. They're going to be flipped onto the positive axis, and they're going to be ascribed not just the positive version of that number, but the positive version of that number squared. So they're going to be firstly flipped onto the positive axis, and then they're also going to be stretched out providing they're greater than 1, or they're going to be stretched in if they're less than 1. Okay, so that's intuitively what this mapping is doing. It is mapping all of these numbers onto new numbers, and we want this new probability space here to inherit the old probability space there. So how do we modify the PDF for this new random variable here? Well, think about what the PDF means. The PDF tells you, remember what it means. It means if you take a tiny little interval, delta x here, so let's call this some tiny little interval, delta x, then the probability that of the event delta x happening, i.e. if you consider this set of points in delta x, so if we consider the set, let's say, what is it? Let's just write it as an interval. The set, let's say this is a point x, then if we consider the interval x to x plus delta x, then the probability of that interval, so if we call this this probability space omega prime, f prime, and p prime, if we take p prime of that interval, then it is approximately equal to, it converges on being equal to, the smaller you make delta x, it's approximately equal to the PDF, which is, I'm going to denote as, phi of x, lowercase phi of x, times delta x. That's what it means to have a probability density function. It's not the probability, it's what you multiply by the length of your interval to get the probability, basically. It's a ratio between the probability measure and the measure on the real line, effectively. Okay, but if you don't understand what that means, don't worry. So just think of it as this density function. Okay, when we, I need some more paper, and we can't go onto that side, so I'll go up, get another sheet of paper. Right, so when we take this function, what we are going to do, when we take z squared, we're going to send all of these negative numbers, we're going to map onto the positive number, and also we are going to stretch out this axis, so points like 2 are going to be mapped up to 4. Sorry, they're not going to be mapped. Yes, it is going to be mapped up to 2. Oh dear. So it's going to be sent to its number squared. 1 is going to stay the same, and any number below 1 is going to get stretched this way, so it's going to get stretched the opposite way. So any number greater than 1 is going this way, any number less than 1 is going that way, towards 0, and all of the negative numbers are being mapped onto these positive ones. Okay, so now what we want is, we want a PDF, which we know is going to intuitively look something kind of like that. And we want the PDF, so let's call this new PDF just f of, I'll put z squared down there, or as a function of little x. We want, if we multiply this by some tiny little delta x, we want that to be the probability that you're within this little region, delta x. But the problem is, okay, so how are we going to work that out? Well, it's going to be, if we could, if we take this point, let's say this is, I want to change this variable, let's say this is, let's say this is x prime as a point here, and basically, what we want is, what is the probability of this little interval here, but we could take x prime back into what it was prior to this function acting. So basically we could take the square root of x prime down here, like that, and that would map us onto the point that was mapped up to x prime by this mapping where we took the z squared. So we took this point here and squared it to get to, I don't know why I've drawn it over there, to get to this point. Now, what we want to know is that's where that point came from. Now what we want to know is, where did the point x prime plus delta x come from? And the problem is, it did not come from the square root of x prime plus delta x. That is wrong, because what you have to do is you have to take account of the fact that you have to square this to get this. So really it would be the square root of this. However, there's a cleverer way of doing that, because if delta x becomes really, really small, then we can use derivatives, basically. We can say that the ratio between a tiny little delta x in here and the ratio, I should have called this delta x prime maybe. So this is a delta x prime in this codomain of this function z squared. And basically, if delta x is very, very small, the way of converting to delta x prime is to say that delta x prime is approximately equal to d, let's say x prime, dx times delta x. So basically the way of converting the ratio between a tiny little delta x and a delta x prime is going to be connected by the derivative, and in this case x prime is given by x squared, so the derivative is just going to be equal to 2x. So let me say dx prime, and I'm sorry I've used the notation x prime. That's really bad, because obviously you think that was a derivative, and now we're taking the derivative of x prime. Do not write x prime prime. I should have put x bar rather than x prime, so this is all going horribly wrong, this explanation. And basically, I just want to give you some more intuition as to why that's true. What we have here is, if I put x down here and x prime down here, remember x prime is now this axis here. And if I take, this is the x-axis here, if I look at this function, it's basically like this. So I'm mapping every point of x onto a value of x prime over here. This is the x prime axis here. So I think of this as being over here, basically. Oh dear, and that's not even on the page. Right, so we're viewing this function here now, and if you take some tiny little delta x in here, then if it's small enough, you can view this function as basically being a straight line like that, and the gradient of that is the tangent. So if you want to know what is delta x prime here, delta x prime, then basically delta x prime divided by delta x is going to approximately be the tangent of the curve evaluated at x. So this is approximately equal to the derivative of x prime with respect to x, which tells us that delta x prime is approximately equal to dx prime dx times delta x. So in this case we'd fill this in with 2x delta x. So delta x prime would approximately be equal to 2x delta x. Okay, so if I now want to work out what the probability density function is, then I use this fact that if I take fz squared of x times delta x, then that should be the probability density function here, which is, we'll just call phi, evaluated at the square root of x. And again, I've switched notation again. I should have left this as x prime. So the square root of x prime. So that's just saying, okay, take your value x, return it back here. Now the square root of x will only map you onto the positive value. Of course, there's a negative value over here which perfectly corresponds, which is going to be mapped onto, so we'll call this negative of x prime, which will be also mapped onto x prime by this function squaring it. But we'll take account of that by just sticking a 2 in front of it at the end. Okay, so don't worry about that basically. The square root is just going to map you onto the positive one. Right, and then what we need to do is take account of the fact that we don't want to just multiply this by delta x prime. Instead, what we want to multiply it through by is the delta x corresponding to that, and that's going to be the delta x is equal to delta x prime divided by 2x. So let's put that through, delta x prime divided by 2x. But we want x in terms of x prime, and we know x is the square root of x prime, so if I just substitute in the square root of x prime, then basically what I can do is then cancel delta x prime, and I'll find that the... oh, and I should have obviously put the 2 in front of there, because the... forget the... imagine I haven't cancelled it for a second. What this works out, before I put the 2 in there, what I'm doing, just to recap, is I'm taking, in fact I'll draw a whole new picture, I'm taking this random variable which is normally distributed, and this is on the line x. I'm squaring the line x to get x prime, so I only now am considering the positive ones here. I will get, this will be distributed in the way mirrored by this, so it will look something along the lines of that, okay? I'm now asking what is going to be the probability density function of this here. What is this graph going to be? And basically this is going to work out such that if you take a little x prime here and you take a tiny little delta x prime, we want f of z squared of x prime times delta x prime to equal the probability of being in that interval. But we can work out the probability of being in that interval by taking the inverse image of that interval in here. And I'm saying the inverse image of that interval is going to be the square root of x prime, which is the number mapped onto x prime, time the probability that you are in an interval of size delta x prime divided by the square root, or 2 times the square root of x prime. The reason is that that's come from this derivative. The delta x prime is going to be turned into delta x prime divided by 2 times the square root of x prime by this mapping. The reason I've explained up here is that if you take some delta x in here, that's going to go to 2x times delta x in here. So if I take a delta x here, it's going to be stretched out to 2x times delta x in here. So if I take a delta x prime here, what I need to do is divide through by 2 times x to turn it back into a delta x here. But 2 times x is the same as 2 times the square root of x prime, and I want things in terms of x prime rather than x. Okay, so the problem with that is that you're also going to have this bit round here, which is negative the square root of x prime times delta x, well, the same interval. This is delta x prime divided by 2 times the square root of x prime. So if I want the probability that you are in these two intervals, firstly I can just deal with the probability that you're in this interval and times it by 2. So I'll times 2, and the probability that you're in that interval is just the probability density function evaluated at this point, which is the square root of x prime, times the delta x value, which is delta x prime divided by 2 times the square root of x prime. Okay, so that is why this probability here is equal to that. So now all I do is cancel the delta x prime, and I cancel the 2's, and what I'll get is that f of z squared as a function of x prime is going to be equal to phi of the square root of x prime divided by the square root of x prime. Whew. Right, we'll take a break there and we'll continue this video in the next part.